So this will serve as kind of an introduction to graph theory. So I'll just go over some definitions of what a graph is and what a multigraph is. So a graph is basically consists of a collection of points and then connections between those points. So the points are going to be called vertices. Sometimes they're called points, sometimes they're called nodes, but usually in graph theory they're called vertices. And then a set of edges connecting the vertices together will let us know, if the points are connected or not. So a multigraph is a graph that contains either loops or multi-edges. So here's an example of a graph. A graph would have these points. These would be our vertices, here, 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 and here. A loop would be any edge. Well, first let's just talk about edges that go from one vertex to another one. So this would be maybe what we call a standard edge. They're labeled in black. A loop would be any edge that starts at a vertex and ends at the same vertex. It doesn't connect two different vertices. And a multi-edge would be if there's an edge that connects two vertices together and then there's another one, so there's some redundancy. And this may come up in communication networks. Maybe you want to make sure that there's a connection between these two nodes. If one of the connections drop, you still have a backup. So you may want to have multi-edges. So any graph that contains loops or multi-edges is called a multigraph. If it doesn't contain those, then it's not a multigraph. Okay. Then once we have a graph, so we'll typically label a graph by using the letter G and saying it's made up of two components, the set of vertices and the set of edges. And the idea of a subgraph would be if we were to take a subset of the vertices and or a subset of the edges to create a graph from the original graph. So let's say this was our original graph. Then the ones that are colored in red can make up a subgraph, which is actually drawn right here. So here we have 4 vertices from our original graph, which had 5 vertices. And then we take a subset of the edges that connect the subset of vertices. So this would be considered a subgraph of this graph. Okay. Then the degree of a vertice would be the total number of edges that are incident on that vertex. So here's a graph where it's a bunch of vertices, and the vertices are labeled with their degree. So for example, this vertex has no edges incident on it, so it's a 0. This vertex is connected to 1 edge. This vertex is connected to 3 edges, so it has the label 3. This one's connected to 3 edges, and so on. Okay, so now we're introducing the idea that we could label our vertices if we wanted to. They could have unique names or not unique names, depending on what the application is. And we have the idea of the degree of the vertices. So connectivity between points in our graphs there's different definitions for them. So one is a walk in a multigraph consists of an alternating sequence of vertices and edges. Like you're at this vertex and you take this edge to get to this vertex, and then you take this edge to get to this vertex, and you're hopping from vertex to vertex. So you're starting at vertex 0 and you're ending at vertex n. So a walk would be where each edge incidented on all the points between them. If there is a walk from 0 to n, we say that 0 to n are connected. So it would be a path that you could take from one point to another. A trail is a walk where all edges are distinct. So in a walk you can repeat the edges again. But a trail would be a distinct set of edges. And a path is a way to get from one point to another where you don't repeat vertices over the way. We would officially call that a path. And then a graph G is connected if for all pairs of vertices you can get from one vertex to another. So, So for example, this graph would not be connected because you can't get from these vertices to this 0 vertex. So this would be considered not connected. But without that, this would be considered connected. You could get from anywhere to any other vertex. Okay. Then the connected components of a graph, if a graph had many components to it, the connected components of a graph would be all the subsets of vertices that are connected to each other. So, for example, this 7 would be a connected component. It's one vertex and it's connected to itself. 6 and 5 is a connected component. And then 0, 1, 2, 3, and 4 is a connected component. Now, if you were to say, for example, 0, 1, and 4, we could see that 0, 1, and 4 are connected to each other. But we wouldn't call this a connected component. We can consider that a subgraph of the overall graph, but it's not a connected component. The connected component is, the definition of a connected component is a connected subgraph that is not contained in any larger subgraph. So 0, 1, and 4 is contained inside 0, 1, 2, 3, and 4. So it's a subgraph, but it's not a connected component. Okay. So a cut point in a graph is any vertex that if you were to remove that vertex, and if you were to remove it, you would also be removing any edges connected to it. That would turn your graph into, it would create two separate connected components. So for example, the points E and X would be considered cut points. And the point Y would also be considered a cut point. If we removed Y, it would make the point W separated from the rest of the graph. But an example, C would not be a cut point, a Z would not be a cut point. If we remove this, which means these two would be gone, this would still be connected. So Z won't cut the graph and turn it into extra connected components. Similarly, if you remove B, A and, if you remove B, B would be gone. The remainder would still be one big connected piece. So those would not be considered cut points. Okay. Then still more definitions. So the distance and diameter of a connected component, the distance between vertices U and V of a connected graph, which is written as D, U and V, the distance between U and V, is the length of the shortest path. The diameter of a connected component is the maximum distance of any two of the vertices. So it's the maximum of all the shortest paths. So for example, in this picture, the diameter of this graph would be 4, and the reason is because the path from 7 to 2, or 2 to 7, is of length 4. So from this node to this node. So we could go 1, 2, 3, 4. There's a couple ways to do it. 1, 2, 3, 4. There's also a longer way of going like 1, 2, 3, 4, 5, 6. So the definition for diameter is not what is the longest path from one point to another, but it's the longest path of all the shortest paths. Does that make sense? That you want to say for every pair of points, whatever the shortest path is out of all the paths from any point to any other point, then take all of those. Whatever the longest one is, that's the diameter of the graph. So it's kind of recursively, diameter is based on the distance. So the distance is the shortest path between any points, and that diameter is the longest of all the distances. So it's the longest of all the shortest paths. Right, so don't just find like the longest possible path from 2 points and say that's the diameter. Okay, then this was a famous Bridges of Königsberg problem. So the idea goes like this. So there's two pieces of land with a river between them. So you could be on the piece of land A, the piece of land B, this little island C, or this island D. And the idea is, can you, starting anywhere, walk over every bridge exactly once? Is that something that you could do? So you could start at B and walk over this bridge, and then go to here, and from here, and go here, here, and then you have 2 more bridges to go over. So is there any way you could start somewhere and finish anywhere you want? You don't have to form a cycle. You just have to walk over every bridge one time. Yeah, so it's a brain teaser, and legend has it that Euler, in calculus, the little number e,
Yeah.
e is 2.71, it's the inverse of the log, the
Yeah.
derivative of the log. So it's named after Euler, that's why it's the little e. And so legend has it he solved this. This is some town in Persia or something that had these islands and bridges. So just look at, does anyone have a guess if you can do it or can't do it? Or?
Could you go from V to D to U? To U.
Well, cross over U.
Yeah, and then go, crap, never mind.
Depends.
Oh, actually then P to S to R to, Q to S to R to P. Fuck, never mind, because then you have to go miss T.
Can't get to
D to D. D to V.
So I guess one way to solve this is, wait, did you have a method? From where?
D to D. D.
P? B?
D to D.
Which one? P?
D.
D to B.
D to B. Over here.
C to D. C.
C to D.
Then D to B.
And then you have to go over one of these two. I guess it doesn't matter. Get to here.
It's right all the way to E. A.
Well, you could come through here, but then you miss this bridge.
Well, what about S to Q, then U to T to R?
So starting here,
Or his method, oh wait, where did he? Crap.
And you walk all the way around from E across.
Then you get a jetpack and you skip over.
Go Batman.
okay, well anyway, so, alright, so there's, continuing on that question, so we'll start thinking of some facts about graphs. Okay, a traversable graph, such a walk must be a trail since no bridges can be used twice. So, okay, so if we were solving that last problem, we would have to find a walk that never uses a bridge twice. Okay, so a graph is said to be traversable if it can be drawn without any breaks in the curve. So if you could draw it all as one big line without repeating any one of the edges. So for example, this graph is traversable because you could draw it by, let's say, starting here. So basically, can you draw the whole picture without lifting your pen off the paper? So you could kind of draw it like this. Right? You could, I guess you could start here and go like this.
Yeah.
Like that, and draw the whole picture without ever taking your pen off the page. And if that's the case, then you hit every bridge, right? Some graphs are traversable and some of the graphs are not. Okay, so we'd have to have a graph that is traversable. So if we can solve this question, this would have to be traversable, that we could put our pen somewhere and hit every bridge without lifting the pen, right? So, so the total degree, so if we were to sum up the degree of every vertex of any graph, must be an even number, right? Because if a graph consists of a bunch of points, let's say you put a bunch of points down first and then you start adding all the edges. Every time you add an edge, some vertex goes up, two vertices go up by 2, what its degree is, right? So you put out all your vertices, they'd all have degree 0, then you add an edge. Now, 2 of your vertices went up by 1. So since 2 of them keep going up, the total of all the degrees of all your vertices has to be even, because each edge has 2 endpoints, right? All right, so and we add 2 every time we add an edge. So the total number of the degree of all your vertices together must be an even number. Okay, so a graph can have some vertices that are degree odd and some that are degree even, right? But the number of vertices that have odd degree have to be even, right? Because the total degree has to be even. So let's say you have a bunch of vertices that are even degree. You add those up, that'll add up to an even number. Then you have a bunch of vertices that have odd degrees. Well, there has to be an even number of them, so that will add up to an even number. Okay, so that's another side. Okay. The total number of odd degree vertices must be even. So you could have 2 odd degree vertices, or 4, or 6. But you can't have 5. Because then your overall graph would have odd degree, but it can't, because every edge has 2 endpoints. So if a walk that used every edge started at an odd degree vertex, then what could you say about where that walk is going to finish?
I'm sorry, can you repeat that?
So if you had, let's say you had a vertex that had degree 3. So a vertex has 3 bridges coming out of it. If you started at that vertex, you would go over one bridge, at some other point come back over a bridge, and then go out the 3rd bridge. So where would that walk finish? Either at that vertex or at some other vertex.
Yeah. It would finish at some other vertex.
Right, if the degree is odd, and you started at that vertex, you would have to finish somewhere else if you want to hit every bridge once. And what if a point had odd degree and you didn't start there? Then where would you finish?
There, right?
You would have to finish there.
Yeah.
Because at some point you're going to walk into it, you're going to leave, and then walk into it again, and then you can't leave. So, for a walk to use every edge, if it didn't start at an odd degree vertex, then it must finish there. So if the graph has 2 odd degree vertices, you would have to start at one of them and finish at the other one. Right? There's no other way you could do that. Right? And if it has more than 2 odd numbered vertices, like 4 of them, it has to have an total even map. But if it had more than 2, let's say it had 4, then you wouldn't be able to do the walk, because you wouldn't be able to start and stop at 4 different places. So this picture of this, this land on both sides of a river plus 2 islands in the middle of a river with these 7 bridges could be redrawn by this graph, where the vertices are pieces of land. So this is one side of the river, here's the other side of the river, here's one island, and here's the other island. And then we just put the bridges as edges in the graph. So here you can see this vertex is degree 3, this one is degree 3, this one is degree 3, and this one's actually degree 5. So this island in the middle has degree 5. So since all 4 of the points have odd degree, if we were to do a walk and hit every vertex, we'd have to start somewhere. Wherever we start, we'd have to finish, without a doubt, somewhere else. But the 3 other vertices, since we didn't start there, we would have to finish there. But we can't finish in 3 different places. We can only finish in one place. So for a graph to be traversable, it either has to have all vertices have even degree, or have exactly 2 odd degree vertices. And you'd have to start at one and you must finish at the other one. This one has 4 odd degree vertices, so you couldn't traverse it. So, yeah, so Euler gets credit for pointing that out.
So you couldn't do this?
Yeah, you can't do it because it's really this, you're taking this, you know, piece of geography and turning it into this graph, and then you're saying, you're noticing that there are 4 odd degree vertices. And if you were to start your walk from any one of them, you would have to finish somewhere else. If you start at an odd degree, you know, you walk out, you come back in, and you walk out. You'd have to leave, you'd have to finish somewhere else. If you don't start at an odd vertice, then you must end there, because you would come in, go out, and then come in, and then you're done. So this graph would have the property that wherever you started, you have to finish at all 3 other places, which you can't do. Yeah. So just, you know, like a little example of how, you know, looking at properties of graphs, you could actually, if this was a bigger, more complicated picture, you might be able to look at it before you start spending hours writing a program to solve it. You might be able to prove it can't be solved, so then you don't have to write the program. Okay. So an Eulerian graph, not a tough thing to say, is a finite connected graph where every vertex is of even degree. So there's no odd degree of vertices. Like that last graph had 4 odd degree points. If every vertex has either degree of 2, or degree of 4, degree of 4, degree of 4, 4, and they're all false except this one being a 2. So that would be an Eulerian graph that has that property. And then a Hamiltonian graph is a graph where, so a Hamiltonian cycle, for example, is it's a closed walk, meaning starting at one point and finishing at that same point. A Hamiltonian cycle is a closed walk, which includes every vertex in the graph. Every vertex gets visited at least once. Such a walk would be a cycle, and therefore is called the Hamiltonian cycle. Any graph that contains a Hamiltonian cycle would be considered a Hamiltonian graph. And then one side definition would be a Hamiltonian path. That's where you start at one vertex, you visit every vertex, but you don't have the rule that you have to finish at the one you started. So for example, this graph is Hamiltonian because it contains a Hamiltonian cycle. So the Hamiltonian cycle is in red. You can see the difference between the red and the black, but the Hamiltonian cycle, let's say we started at F, goes like this. So we hit every vertex and finished at the point where we started. So this would be considered a Hamiltonian graph because it contains a Hamiltonian cycle. Here's a graph that is not Hamiltonian, but happens to contain a Hamiltonian path. So a Hamiltonian path means you start somewhere, you finish somewhere else, and you visit every vertex. So we have this path, and we visited every vertex. We could come back. We could come back. So this would actually be a Hamiltonian graph. But that's an example of a Hamiltonian path. You visit every vertex, and you don't have to finish at the one you started at. Okay. Then a couple of other definitions that come up somewhat often in computer science is a graph is k-regular if every vertex has exactly the degree k. So for example, these two graphs are 3 regular because every vertex is degree 3. 3, 3, 3, 3, 3, 3. Every edge has 3. Same thing here. So these are 3 regular. We could also say a graph is K23, meaning it has 2 parts. It can be broken up into these 2 pieces are degree 3, and these 3 pieces are degree 2. We call that a K23 regular graph. Or same here. So we're creating a partition in the graph. And then here we have two parts that are degree 4 and 4 vertices that are degree 2. So that would be a K24 graph. Okay, then, again, we're still doing more definitions. A bipartite graph is a graph where if you could break up the vertices into two distinct subsets, such that every edge in the graph will connect a point from one subset to the other subset. So, for example, the red dots here make up one set of vertices, and the blue dots make another one, and then every edge connects a red dot to a blue dot. Now, it's sometimes easy to see if you put all the dots on one side and all the dots on the other, and all the lines go between them. It's sometimes easy to see. But a graph like this, you could also see there is a way to break up the points into 4 red ones and 3 blue ones. And now every edge in the graph connects a blue point to a red point. So if there's any way to take all the vertices and break them up into 2 subsets, such that every edge will connect a point from one subset to the other, then that's a bipartite graph. Okay, then other cases of special graphs is a tree. So a tree is basically defined by any graph that does not contain a cycle. It doesn't have to be a Hamiltonian cycle. It doesn't have to be a cycle that hits every vertex. It could just be any cycle. If there's no way to walk from one point back to itself, the graph has no cycles. And a graph that has no cycles is called a tree. So in computer science, they call it a tree, and it ends up being, you know, so here's an example of a tree that kind of looks like a Ferris wheel. Here's an example of a tree that actually looks like a tree, right? So we have, like, you know, the what's it, the bark? What's the
Trunk.
The trunk of the tree. Okay, we have the trunk, and then we have like kind of leaves going off. But in computer science, trees will almost always look like this. They will always look like, they won't look like a tree. They'll look kind of like an upside down bush. So the textbook should refer to it as an upside down bush, not a tree. But so you'll probably see pictures that look like this a lot throughout your computer science courses, and they'll call that a tree. But it's really like, you know, a tree kind of goes up tall and then spreads out. A bush spreads out right from the beginning, and this is kind of like an upside down bush. But they call it a tree. So anyway, you have a collection of vertices and edges, and there are absolutely no cycles anywhere, that would be called a tree. So a graph that is cycle-free or acyclic is another way of saying a graph that is a tree. Okay. Then we have the idea of labeled graphs. So we can label the vertices, and we can label the edges in some meaningful way. We would then have a labeled graph. And what's pretty common is to label the edges with values. If you happen to label the edges with values that are non-negative, 0 or positive numbers, then we would generally call those labels weights. So it would just be an amount that would be some kind of cost that if you were to take that edge. So here's an example of a labeled graph. The vertices are labeled with letters, and the edges are labeled with numbers. Okay. Then another special type of graph is we could say that 2 graphs are isomorphic to each other. If there was a way to take, so if we have this graph, if there's a way to say, can I create another graph? Or if you happen to be given 2 graphs and you're being asked a yes or no question, is this graph isomorphic to this one? So in other words, for every point in this graph, let's say here's 1, can one of these map to that one and be connected to exactly everything it's connected to here? So for example, if I was to say vertex 1 in this graph maps to vertex A in this graph. Now I have to make sure that vertex 1 is connected to what I'm mapping this vertex to in this graph, which would be vertex H. And then I have to make sure this one's connected to this one, so this one must be connected to this one. If this one is connected to some other vertex, that would be like this one. So in other words, you're creating or checking that there's a match, that every single vertex here has a corresponding vertex here that is connected to or not connected to every point so that they match exactly. Then we would say that this graph is isomorphic to this one. So if you had to write a computer algorithm for doing that, there'd be many, many combinations of doing this. You'd have to say, okay, I'm going to let this point be this one. You know, you could enumerate every permutation of every combination of points and then check, but we might want to find an algorithm that can do that faster. And that finding out if a graph and a subgraph are isomorphic does things like facial recognition software. You're looking for matches within pictures of each other. So this ends up being a big field, taking two graphs and finding, can something match something else? Is there a match within a graph? Then another special graph is a rooted tree. Not a big deal, it's just take a graph that is a tree. You can pick one node and say this is the root of the tree, which generally means it's a starting point when you go looking through that tree. And then, since there's no cycles, you keep getting further and further away from the root until finally you can't go anymore. So the nodes that have no more ancestors to go to, those are referred to as leaf nodes. And then anything between the root and a leaf node, any node between them would be called an internal node. Okay, then a planar graph, or a planar graph, so a graph or a multigraph that can be drawn on a plane without any edges crossing each other would be considered a planar graph. So a subset of all graphs are planar graphs. So for example, this graph is planar. Even though these two edges have crisscrossed, you could take one of these edges, let's say this one, and just draw it around the back here, like that. So that's really the same picture. Right? They didn't have to crisscross. We could have drawn it in a non-crisscrossing way. Could also draw it this way. So here's another example of a planar graph, but here's a graph that could not be drawn in a planar way. So you might think you could take this one and draw it around the back, take this arc here and draw it around the back. You know, all these internal arcs, but you're going to at some point get a crisscross. So that's an example of a graph that could not be drawn as a planar graph. Okay, now if you had a graph that was planar, a map is a planar representation of a graph. So we could call that a map. So that would be like if you saw a map of the United States, you'd have all the roads between them, but the roads don't have to crisscross each other. Okay, then a region of a given map divides a plane in, a given map divides a plane into various regions. And the degree of a region is the length of a closed walk or cycle which borders that region. So, one theorem in planar graphs, the sum of the degrees of the regions of a map is equal to twice the number of edges. So let's take this as an example. This graph has 1, 2, 3, and then the outside is really a fourth region. So this is a graph with 4 regions to it. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So the idea, this theorem is basically saying the sum of all the regions of a map is equal to twice the number of edges. So we have 9 edges, that's really 18, ends up being this number, 2 times 9. And the sum of all the regions, the degree of all the regions. So all the regions, if you say how many edges are on each one, so this region has 1, 2, 3, 4, this region has 1, 2, 3, 4, this region has 1, 2, 3, and the outer region has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So if you add those all up, you would get the total region is 18, which is equal to 2 times the number of edges. Okay. So, okay, then we get to Euler's formula for a graph. Says that the number of vertices minus the number of edges plus the number of regions will always be 2. And we can kind of prove this inductively by saying that we take an existing graph and we rebuild it from scratch. So if you take an already existing graph, so all graphs start off with, let's say, one vertex. So suppose we had a graph, we picked out one vertex and added it to the graph. So we have one vertex minus the number of edges, which is 0. That gives us one region. So a dot on the middle of the paper is just one big region. So the first case holds. Now we repeatedly pull an edge out of the graph and connect it to our graph. That will either make the number of regions stay the same, so we will add an edge plus a new vertex. Or if we add an edge that really connects two vertices that are already in the graph, then we will have created a new region without adding a new vertex. So the number of regions would go up by 1. So every time we add an edge, this middle number goes up by 1, and either this or this goes up by 1. And it initially started at 2, so it just remains at 2. That's also true for planar graphs. Then there's the idea of colorable graphs. So if we have a graph, if we can assign colors to all the points in the graph such that no two points are adjacent to the same color, then we could say that graph is n-colorable. So here is a 4 coloring of this graph. With as few as 4 colors, we can color all the vertices such that no edge connects two of the same color. So this would be an example of a 4 colorable graph. Okay. Then there's the idea for graphs. We could take a map which has regions A, B, C, D, and E, and we could convert it into a graph where the vertices represent the regions and then the connections are whether those regions border on each other. So you could make this conversion following the colorable graphs. So given a map, you can convert it to a graph, and then edges would just represent whether those regions border on each other. Okay. Then there's the idea of a directed graph. So that would be where the edges have an orientation to them. So this is basically saying A is connected to B, but B is not connected to A. So if you think about it, an undirected graph, which doesn't have orientations, it's kind of like you have 2 arrows. A is connected to B and B is connected to A. So any undirected graph can be easily converted into a directed graph by every time you see an edge, just put 2 arrows going in both directions. Okay. Then the spanning tree of a graph would be, if you were given a graph and you are asked to find a tree. So you could have a graph that has cycles in it. It doesn't have to be a tree. But now your goal is to find a tree that would be a subset of the edges, but with every vertex, such that the tree is touching every vertex in the graph. So we have the original graph with the thick and thin lines, and then the thick lines are the spanning tree. So for example, every vertex is covered by a thick line, and the thick lines represent a tree, no cycles. And then the idea, if they have weighted edges on them, you might even want to, so first of all, you can realize a graph could have many spanning trees, right? Not just one. But out of all the possible spanning trees, we could write every permutation of every spanning tree. An interesting one might be the one that has the minimum weight. So maybe you want to connect all these points and spend the less cost connecting them together, so you might want to find the minimum spanning tree. So sometimes that's a special spanning tree. And that would be a harder one to find than just a general spanning tree. A vertex cover is the similar idea. A vertex cover would be where you have a graph, and instead of, like a spanning tree, picking out a subset of the edges that connects everything together, we're now going to pick out a subset of the vertices. So anytime you pick a vertex, you get for free all the edges connected to it. So we want to pick a subset of the vertices so that every edge in the tree is covered. So with 1, 3, and 5, we will hit every edge in the graph. So 1, 3, and 5 would be a vertex cover of this graph. with 1, 3, and 5, you have a connection to every edge in the graph. Okay, so then the thing is, when you go take your algorithms class, you're going to answer questions like, given a graph, find the minimum spanning tree. Or given a graph, find the minimum vertex cover. And some of these questions, there'll be an algorithm that makes sense to run on a computer, and you code it up and run it. And some of these questions, it may not make sense. The only way to solve the problem would be to write every permutation of the problem and then pick the best answer, which has an exponential running time, and it becomes pointless to run. So some of these questions, like find the minimum spanning tree of a graph and find the minimum vertex cover of the graph. One of these happens to have an answer and you'll code it up, and the other one you would make an argument using graph theory that you can't solve it on a computer. But anyway, to run algorithms on a computer, we have to figure out a way to take these graphs, whether they're directed, undirected, weighted, not weighted, and we have to represent them in computer storage, then run algorithms changing the storage to find the answer. So two of the most common ways of representing graphs in computer memory, one would be a two-dimensional array. So if we have a graph that says 1 is connected to 2, this graph, everything's connected to everything. Everything's connected to everything. Okay, so with an adjacency matrix, we could say we have a 2 by 2 matrix, 1 to 4 by 1 to 4, and you put a 1 there to represent, yes, they're connected or not connected. And I guess we're saying 0, well, 1 is not connected to 1, but 1 is connected to 2, 3, and 4. And in this case, so first of all, in this case, we have redundant data. We actually don't even need half the matrix, right? If 1 is connected to 2, then we know 2 is connected to 1. Here we're actually recording 1 is connected to 2, and we're also recording that 2 is connected to 1. So this line was actually recorded twice in this matrix. In the case with orientation, and sometimes now you have a benefit to it. Here we're saying 1 is connected to 2, and 2 is connected to 1, but 2 is connected to 3, but 3 is not connected to 2. So we can represent that with a 3 by 3 matrix. 1 is connected to 2, 2 is connected to 1, 3 is not connected to anything, but
2 is connected to 3.
but 2 is connected to 3, but 3 is not connected to 2. So now we're using the whole matrix. Well, like I say, this whole part of the matrix really is unnecessary. We only need this one is connected to a number equal to or higher than it. And another way, which might not make sense, but when you take your algorithms class, it's much more popular to do this because it makes your algorithms run faster. For every node in our graph, we want to maintain not a matrix, but a linked list of what they're connected to. So for example, node number 1 is connected to 2, and 3, and 4. So we'll maintain a linked list of everything it's connected to. So we'll say we're connected to 2, and then we go for the next one. What else are we connected to? 3, and we're also connected to 4. And then node number 2,
3.
oh yeah, has a two-way arrow. Okay. So 2 is connected to 3. So we go to 2 and we just start walking down this linked list, looking for what it's connected to, and it's only connected to one thing. So the slash means there's nothing else we're connected to. So this is a linked list. You learn in your data structures class how to create a linked list and just keep adding links for everything you're connected to. So it might seem like, does one seem better than the other? This one's a little more intuitive, like your mind says, okay, yeah, I have a matrix, what's connected to what? This one also captures the data, but the one advantage to this is if your map gets very, very big and you just want to know what you're connected to, it might be faster to just record the things you're connected to, not having to search everything you're connected to and everything you're not connected to. So it could save time. If you went out to your data structure to say, what's in my graph, to say what is 2 connected to, yeah, well, let's say there was 100 nodes. and you wanna know what node 2 is connected to, you'd have to ask, am I connected to 1? No. 2, no. 3, no. 4, yes. No. 5, no. 6. So it's a lot of checking just to figure out what you're connected to. Whereas if you only had a linked list with what you're actually connected to, you might be able to hit it much faster. So this is more intuitive, but this is the one that ends up being used a lot more in your algorithms class.